Hopefully it's recording, and as always, can I ask the question, can you see my screen? Can somebody turn their microphone on and call out? Makes it easier for me.
Yes.
Yes.
Okay, great, thank you. I'm not going to make the slides extremely large because I always run into problems when I do that when I'm switching between screens. So I'll just leave them in this mode. I indicated last lecture that in the past, many students have found some of the material in today's lecture to be really confusing for the first time. And that often comes about for students who are not really confident with recursion. So I'm going to work through the recursive algorithm fairly slowly and hold your hand stepping through it, because I think it's a really important thing to be on top of, and we need it for later on in the semester. So that's our plan for today. First off, I've made a comment that if you have to write an algorithm to solve a problem, you really have to understand how the algorithm works, or what are the requirements. So the focus of today predominantly is going to be on graph traversal methods. Traversal methods being moving around the graph, possibly looking for a particular key value. And as I indicated last lecture, there are two well-known algorithms which we use, breadth first and depth first. And at the end of last lecture, I put up a sample graph and stepped through them remarkably quickly. And when I give this question to you guys, here's a graph, go and use breadth first search or depth first search. Everybody can do it, right? And you can expect that that's going to be a 2 marks out of 60 on your final exam. I'm going to give you a question such as, here's a graph, and I'm going to ask you to trace it using breadth first search and depth first search. And 98% of you are going to get full marks on that question. I'm going to step through that in just a minute, but read the very bottom line of this slide. Everybody will be able to trace the algorithm for breadth first and depth first search, but it's a lot more challenging to be able to write it in pseudocode and to write it in an efficient, easy to understand algorithm as well. So let's step through a breadth first search algorithm first, then a depth first search, and then we're going to start looking at the code. So here's my graph. When I look at my graph, if I'm going to use breadth first search, I'm always going to start at a particular node. By default, if I don't specify a node, we're going to do things in alphabetical order. Just a rule I'm imposing on you guys. So I'm going to start at A. And you will notice in my graph I've drawn here, I've put it in this hierarchical nature. In fact, it's a tree. But when I do breadth first search, what happens? I scroll through in this level mode. So I start at A, and I always ask the question, who are my neighbors? And then I'm going to visit the neighbors one step away from me using whatever method I like. And I'm going to say, I'm going to do it by default in alphabetical order. Once I've done it at level 1, I then go and do it at level 2. So I'm 2 steps away from A now. And then I'm going to do it at level 3, all the way down until I finish. So the breadth first search, I'm always asking the question, who are my neighbors? At level 1 step away. And then once I've done it at 1 step, I do it at 2 steps. So I've got a question mark here. And what I've done at the bottom of this slide is written down the order that perhaps I get when I do a breadth first search. So I started at A, level order, then I went to B, then I went to C, then I went to D, then I go down to the next level. I went to E, F, G, H, I, then I went down to J. It's a breadth first search. I'm sure all of you guys can trace that. Now the obvious question, go and write an algorithm to do it for me. And that algorithm is going to come up in about 10 slides time in the lecture slide. So we'll come back to it. This time, we're going to do it as a depth first search algorithm. Using the same rules again, I'm going to start at the default node. So I'm going to start at A. And this time, when I trace the algorithm, I'm not going to do it level by level, but I'm going to go down one path as far as I possibly can until I reach the end. When I reach the end, I'm going to turn around and backtrack. So when I started A, I'm going to follow this path. And by default, the argument I'm using is, who are my neighbours? The neighbours of A are B, C, and D. I pick one of those neighbours. The rule I am imposing is, let's pick them in alphabetical order, just so we all get the same answer. When I go from A down to B, all good. Now I ask the question, who are the neighbours of B? They are E and F and A, but I don't want to go back to A because I've already visited A. So I'm almost asking the question, who are my new neighbours that I haven't visited before? So that was E and F. So I go down and visit E. E doesn't have any neighbours apart from B, and I've already been to B. So what happens? Oh, I need to go backwards to B. But when I go backwards to B, that's all good. When I asked that original question before about who were B's neighbours were A, E, and F. I haven't visited F yet. So now I'm going to visit F. And similarly, I'm going to get down to J. When I get sick of it, I reach the end, no one else to visit. What happens? I have to go backwards. I've already visited these guys, so eventually I'm going to end up all the way back at A. Now, who were the neighbours of A? Neighbours of A were B, C, and D. I'm going to visit them in alphabetical order. I've already been to B, so now I'm going to go to C. And that sort of process. And I keep going and going. So what I've written at the bottom of this slide is what I think might be the depth first search order if I visited these nodes. And is that list correct? So I'm saying I'm going to visit A to B to E to F to J to C to D to G to H to I. I think it might be right. Can somebody call out if I've made a mistake? I didn't deliberately make a mistake. I possibly did. Is it correct? Let's find out.
Correct.
Few people confident. Okay. I would hope, so there you go, guys. I've just given you a charity 2 marks on your final exam. I'm going to ask you to do that, absolutely guaranteed. Now, this is far more important. I want you to be able to write an algorithm to do this depth first search. So if I'm going to do this algorithm for depth first search, I need to think a little bit more about what's going on. This time I've drawn the graph, but rather than making it look like a tree so it was really easy to see what's happening, you've got to think about it just a little bit more. So I have 7 nodes, is that right? A, B, C, D, E, F, G. It looks like I've got a whole lot of things, but there's a couple of words in red here. What I'm going to do with my depth first search or my traversal methods is I'm going to keep track of which nodes I've actually visited before. So I'm going to start at A. So if I've already started at A, I don't have to go back and check it again later on. And when I was talking about backtracking, I go as far as I possibly can, and then sometimes I've got to turn around and come back again. So this depth first search order at the bottom of the screen, I would hope that most of us can get that answer right now. What we're going to do is look at how Levitin introduces an approach to do this, and then we use this as the basis for how we write our algorithm. And the text at the top is extremely important. The logic inside the algorithm is similar to how that stack worked when we were doing a factorial. So if you think about when I had a recursive algorithm for factorial, I went through that process of saying, I couldn't do 4 factorial until I could do 3 factorial, and I couldn't do 3 factorial until I could do 2 factorial. And I build up a stack. And then I take things off the stack and then I can solve the problem. So using that sort of idea, what's going on? If I look at all of these letters of the alphabet at the bottom half of the screen, on the left-hand side, all I'm talking about is you have to start somewhere in the graph. So by default, we're going to start alphabetical order. The next question I ask is always the same. Who are the neighbours of A? The neighbours of A are B, C, D, and E. I am going to choose one of those neighbors. And by default, just to make it simple so we all get the same answer, I'm going to pick them in alphabetical order. So this next item in the stack is just telling me the next item I visited. So I've gone from A down to B. Then the next question is, the question in effect is the same. Who are the neighbors of B? The neighbors of B are A, D, and E. Which one am I going to visit? I do not want to visit one of those nodes that I've already visited. So I don't want to visit the A. So I'm going to pick the next unvisited node. And by default, the alphabetical order, the D. So I'm building up this stack. When I build up the D, I ask the question again. Who are the neighbors of D? The neighbors of D are A, B, and E. And please correct me if I make a mistake here. I'm not deliberately trying to make a mistake. So that's where the next stack value came from. Now, if I concentrate on E for a minute, I'm going to ask those questions again. Who are the neighbors of E? The neighbors of E are A, B, and D. But guess what? I've already visited all of those guys. So in effect, I've got to the bottom of my depth first search tree. So I'm going to say, I'm going to go backwards now. So when I start backtracking or going backwards, it's the same as taking it off the stack. So I take it off the stack. Now I'm back at D, going through that process. Well, I've already visited here, so I have to take it off the stack, take it off the stack. And now I'm back to A. But now I'm asking myself that same question again. Who were the neighbors of A that I haven't visited already? And C happened to be that guy. So that's where the C comes, and I push it onto the stack. Does C have any neighbors? No, so it's time to backtrack. When I backtrack, I take it off the stack. And because this was a disconnected graph, then I have to complete the rest of the process as well. So the next slide is just a shorthand representation showing me exactly what I just did. So if you look at those numbers, the first index next to the A, B, C, that is the order in which the values were added to the stack. The second column, or the second index value, is the order in which the items were removed from the stack. A was added first, B was added second, D was added third, E was added fourth, C was added, let's have a look on the next slide, C was added fifth. Where did these numbers come from? The 1, 2, 3, 5 on the right-hand side. It was the order in which they were removed from the stack. I'm not going to go to that one. I'm going to stop sharing my screen for a minute and just look at my chat window. Does somebody have a chat popping in? Can I write it in Python? We're going to do lots of things in Python possibly. If that question was about the assignment, I'm not going to answer that one just yet. And I'm not going to answer any more on chat just at the minute. Right, back to sharing my screen again. Back to my slides. Okay, we've got this general idea. Did I click? I had too many then. I think I might have. No, I didn't. Right, back to this one more time. Leviton's representation of this stack discipline is fundamental to how the algorithm is implemented. So we need to make sure we're clear what's happening there. And when I go to the next slide, these numbers of the order in which they were pushed onto the stack corresponds to that depth first search process that we're going to be using. This diagram is just talking about that general nature of the tree of what we're searching for. And I'm going to refer to that as a depth first search tree. So the black lines, the black edges are corresponding to real edges in the graph. The blue dashed lines are basically corresponding to ancestors, if you like. So for example, A is a direct or is an ancestor of D because, hey, look, there's a link between them. A is connected to E, but I didn't actually go to E directly from A. I went there via B. So the blue lines are just showing this ancestral relationship that actually existed. We'll come back and talk about the tree edges a little bit later on, but at a conceptual level, there's just a link there, but we didn't use it when we built up the tree to start with. So here is our depth first search algorithm. Notice it's only a few lines of code. It is a very elegant algorithm. In fact, I think it's a very, very impressive algorithm. On one of the earlier slides, I said it's built up via this stack idea. But there's nowhere in this slide that I can see the word stack, or I'm not making use of a stack data structure. Yet I've made a claim that depth first search relies on the stack idea. And the reason for that is at the top, there's a function DFS for a depth first search. What it takes in is an argument, which is a graph, V, the number of vertices, the number of edges. Whether it's an adjacency list or an adjacency matrix, obviously is going to change how we process it in some way. I'm going to ignore part of this just for a minute, but then it goes on and says, basically, I'm going to loop through every V, every vertex or every node in that graph, and I'm going to do some stuff with it. Then what I'm going to do is, as I'm doing stuff, which I haven't defined clearly, is I'm going to call this other function DFS explore. And when I look inside DFS explore, it's actually a recursive algorithm. And that's where the stack part is coming into play. So what I want to do now is hold your hand and step through this algorithm. And then we might even look at some of the Python code to see what's actually going on. There's another thing which I haven't mentioned on this slide, and it pops up on the next slide, which is fairly verbose text. So rather than using that slide, what I'm going to do is just talk about what this mark and count might be. So mark is really going to be corresponding to keeping track of these numbers in the traversal stack. So mark is going to be an additional piece of memory, an additional array of size n, the number of nodes. I'm going to initialize it all to be 0, and then I'm going to update the value of that array, that mark array, with the numbers corresponding to the order in which I visit the nodes. So that's what the mark part is talking about. There's going to be a count variable which is used just to keep track of which item am I actually up to. The third line on this particular slide talks about the need to think about whether I'm using an adjacency graph or adjacency matrix or whatever. But the key here is you always have to ask the question, who are my neighbors? And have I visited that neighbor before? The complexity issues at the bottom of this slide, I'm not going to talk about just at the minute. Here's the algorithm again. So 2 parts to it. We start off the algorithm at the top level where we're passing a graph. I'm going to then create this auxiliary matrix, this auxiliary array, which I'm going to call mark. I'm going to initialize it with 0. Then for every node in my graph, I'm going to go through and ask the question, is the mark value 0? That means it hasn't been visited yet. If that's the case, what I'm going to do is start my DFS explore. When I start my DFS explore, I pass in a node. What happens? I increment this counter value and set the value of mark to be corresponding to that value. Then the statement is, now that I've passed in a node into this function, what I want to do is ask, who are my neighbors? And in fact, what I'm saying is for every one of my neighbors, what I'm going to do now is say, have I visited you before? If I haven't visited you before, recursively call this DFS function again with that neighbor. That's the logic of what's going on. So when I look at slide 7, I think it's a little bit confusing, especially if you're relatively new to the recursive algorithms. So what I did was, and this might be a little bit small, I'll blow it up a bit. So just on a bit of paper, I did do it on my document camera, but I thought I'd record it for you guys. I've just drawn a picture describing what the starting point of the algorithm is. So there's nothing special about this slide, right? So I've just reproduced the graph, and the function DFS took an argument, which was a graph, a set of vertices, set of edges, nodes and edges. And what I've done at the top is just made a list of what my vertices or edges were. They were labeled A, B, C, D, E, F, G. When I was looking at the algorithm, it said create this extra matrix, this extra array called mark of size n and initialize it to be 0. So that's what my diagram on the left-hand side is doing. I'm just going to use that mark algorithm to help me keep track to say whether I've visited the node before. So if I visit the node, I'm going to change this value from 0 to a number. It could be just a binary number, but better than that, what I'm going to do is record the order in which I visit them. And that's what a variable count is going to be used for. Over here, I've just assumed I've had an adjacency list representation, but it doesn't matter. You can do it as a matrix. What I've done now is just for each node, I've listed who the neighbors are. So rather than having to go back and look at the picture every time, I can just use the adjacency list representation, or it could be a matrix, because that's what your algorithm is going to be using. Where to start? If you look at the algorithm, it's talking about a node V. So what we're going to do is always start by default at A. So V, which is the node that we're talking about, gets a value of A. That's the first node we're going to process. So mark 0 is equal to 0. Mark 0 is corresponding to mark node A. So that's just initializing the algorithm. Now, if I go back to the algorithm, what I've just said was, I'm in this DFS function. For each V in V, A was the first node. So I'm saying A is that V value. That's what I'm passing into this DFS explore. So the argument is the value A. Down here, so what I'm going to do is increment the value of count. So count now has a value of 1. And I'm going to mark V with count. So that means mark position A, which was mark position 0, becomes 1. I'm going to have a diagram of that in just a second. Then the other part, and this is where we start to think about that stack representation. There's a for loop here to say that each edge VW, V was node A that was passed in as the argument. W is corresponding to each of its edges, each of the nodes which are neighbors of it. In this particular example, they were B, C, D, and E. So when I'm reading this bottom part of the code, what it's going to say now is it's going to ask and check the mark array to see whether these values are zeros. If they are 0, I call the DFS explore function again. So I'm going to pass the B, or the W value is B. So the argument B is then passed back into the DFS explore function. So it becomes the V value. What did I just say using a diagram? Again, this may be a little bit small because I took it from my document camera just before the class. So what happened when the algorithm started to run? We started off by saying for all of the nodes in the graph, all of the V's, the first one was A. I set mark A to equal 0. That happened because I was calling, that was the initialization phase. That was the first one. I call the function DFS explore with A, increment the value of counts, which sets the value of mark A to be 1. So what I've done on this diagram as I've drawn it, I've just listed the node again, listed the neighbors out, and I put a little value of 1 there for the value of A, indicating it was the first one visited. And I've just listed the other neighbors of A. And each of those are a potential W in the algorithm. So the algorithm all comes together. There's lots of little steps involved there. What happens next? What I've done is just drawn the next step out on the document camera and then took a picture of it for this class. So what happened? Because B was a neighbor of A and it had a value of 0, that became the W value, which was passed into the DFS explore function again. So that was the W, which then becomes the V in the argument passed in. Its value was 0. So yes, I am going to explore the B value. That gets updated by the count value to be 2. So now I've got B is equal to 2. Who were the neighbors of B? they were A, D, and E. So they are the potential W values. However, A already had a value of 1, so I'm not going to visit A again. What I'm going to do is visit the D, because that's the next in the list. So using the algorithm, we're going through. The key is in this part here, and I've zoomed in my screen too large. It's this part here that's the issue. And notice how there's the stack representation inside, or the stack representation corresponding to the recursive call embedded inside the for loop. So I continue on, and I'll make that a bit larger again. So I've done the B, get the neighbor of B, which is the D. So the D becomes the V, which becomes the W. Isn't this confusing? I keep updating the values, update my count, and now D gets the value of 3. Again, I ask the question, who are my neighbors of D? They are A, B, and E. I do not visit the A and the B because I've already been there before. I know I've visited those nodes before because of their marked values. The marked values are indicating the order in which I visited. So now I have to visit the E. I go through the process to visit the E. I'm adding more detail each time. So I'm looping through. Now I get to the stage where I'm at that, I've gone as far as I can. How do I know I've gone as far as I can? Because all of the neighbors of E have a marked value which is non-zero. So this is where the backtracking jumps in, where I start to pull things off the stack. So I can't do that anymore. So I'm out of, so there's not going to be more recursive calls. So the recursive calls start to stop. So I'm still thinking about the algorithm to see what happens. I'm at that backtracking stage. What happens when I go through that backtracking stage? Well, I know C was still a neighbor of A. So how am I going to get to process the C? And I'll go back to the algorithm for a second. Need to bring it back again. So in this particular part of the code, so you'll notice that there was a for inside here. So we started off by passing the A in. We asked who the neighbors of A were, and we went through, and the last one happened to be a C, which wasn't processed as part of this particular call. But then the C does get processed after all of the recursive calls because it's embedded, it's one of the edges in this particular for loop part. So that's what happens as I move through. My screen's too large again. So as I move through, I keep going through. Oh, gone too far again. So I can process the C. Sorry, I've get to the stage where I can process the C. It all works fine. So using the same arguments. Then the next step was, because it was a disconnected graph, I'm basically out of the DFS explore function now and back in the original DFS function. And I get to call it again. And that's how the F and the G get processed. Now, based on what I've just said there, I'm going to stop sharing my screen for a minute. There's multiple questions popping up in chat, which are obviously going to be too many to answer right now. So let's have a quick look. There's so many here. So obviously we're using the stack as this last in, first out sort of idea. Could the mark array be bigger than the number of nodes? Yes, it could be, but we're only interested in whether we have visited that particular node or not. I'm not even going to get involved with the jungles. Okay, I don't think there's a particular question that I really need to jump in and answer there. So what I'm going to do at the minute is, before I, oh, what's happened here? Share my screen, sorry. Something's gone wrong. I've got to stop sharing my screen for a second, guys. I want to share some Python code with you this time. Okay, so let's talk about the Python code for a few minutes. Can somebody call out if the Python code's on the screen?
Yes.
Yes.
Okay. So what I've done, as always, is all I've done is taken the code which was given to you on the LMS and dumped it into Jupyter Notebook. So I'm going to start with the test function. The graph was defined in adjacency matrix representation. So before we do it, all I did was draw the graph very crudely, right? So if I look at this particular graph, I would imagine everybody in this lecture could tell me what the depth first search is going to be. So I'm going to go and visit the one, starting at one by default. We're going to do it alphabetically or numerical order. So the node was 1. I'm going to visit 2 next. Depth first search, 2. I've got to visit 4. Then I'm going to visit 3. So the order is going to be 1, 2, 4, 3. Here's the algorithm, just directly off. No problems there. And all I've done is added a print statement to print out the contents of Mark when it finishes. So you can sort of go and run that to see what happens. Now, what I've done is taken, no, wrong one, sorry. It again, depth first search is what I want, I'm sorry. Right, so I've taken this lecture, taken the same program off Canvas, and all I've done is embed a few more print statements in there. And what I've done is drawn the adjacency matrix for the graph which was presented on the lecture slides. So I've got the adjacency matrix from the graph on the lecture slides there. I didn't draw the picture up here, you know what it looks like. And all I have done is added some print statements to print out the contents of this array Mark, which is keeping track of whether I've visited that node before. I've added a print statement to talk about what's the current node that I'm processing. And remember, because I've got this representation, it's not going to print out A, B, C, D, Z's and whatever. It's going to print out the index value into the list. Then in the recursive function, I've added additional print statements to say what's going on. So I've put a comment to say, which function am I in, and printing out which node am I processing, what's the current count value, what's the current contents of the Mark array, because originally it was all zeros, so it's going to increment as we're going. Then printing out every time I go in to see what happens, we can explore in a bit more detail. The syntax here is just a little bit different to the lecture slides because we're definitely using an adjacency matrix in this case. So that's where I have that sort of syntax coming in. So rather than just saying for each edge in whatever, we're just checking to see whether the value was a 0 or a 1. And when I do that, I get the output of this particular program. I'm not going to step through this code with you line by line. I'm just going to run it. And when I quickly scan through that when I quickly scan through that display, if I highlight the Mark values, you can see it updating as we go through. And as you saw when we did our depth first search, we went from A to B to D, so it seems like it's working properly, and eventually we get that output right at the bottom. So conclusion, you don't really need me to sit here and step through that program with you. All I have done is added print statements where I want to know which nodes are being processed to see what happens. You can step through that yourself. What I have to do is go back to the lecture slides again, because we're going to run out of time if I don't get a bit more speed on here. Do you have the PDF documents back again, the lecture slides?
Yes.
Yep. Okay, so conclusion to what we've done. Depth first search is a really, really cool, nice, compact algorithm. It relies on that idea of using the recursion calls, which have the aspects of a stack protocol in play, although there's no explicit stack. How we represent it is really important. If I use an adjacency list versus an adjacency matrix, the complexity is going to be different. And I guess you guys can sort of have a stab in the dark of why the V squared and the V plus E come about. So there's always that trade-off, but sometimes it's easier to represent it as an adjacency matrix, as you saw in our code, because we didn't have to worry about doing all the linked list sort of stuff in there. And remember, Mark is a really important auxiliary array here, keeping track of what's going on. You could have always, if you're using an object-oriented type approach, used Mark as an attribute of a node and just done it that way, and that would have worked equally as well. My last comment, sorry, I'll go back again. So what we did when we stepped through this algorithm, all we have done is the same as what Leviton has done. We've just basically generated that sequence of numbers as we've gone through. And that's what the Mark values actually were. There's 3 questions now, which I'm going to just pose quickly. I'm going to possibly answer 2 of them, but I'm not going to answer the 3rd one. The first question is, if I was to give you that DFS algorithm, how could you modify it or do something to it to decide whether the graph was connected or not? So remember, in our graph, F and G were not connected to the rest of the graph. So how can we determine whether the graph is connected or not? And the simple answer will be, well, did I go back to the DFS function rather than the DFS explore? And we did, so therefore the graph was not connected. So that should be a relatively easy thing to answer. The next question, how can I determine whether there are cycles in the graph? Cycles in the graph would correspond to, sounds like you'd be always going, or you would be going back to mark nodes. So something corresponding with the mark values. So you're really asking the question, is the neighbor marked in some way? So when you're using that recursive loop, if you're heading back to mark values, that's going to be an indication that you've got some sort of a cycle. These questions I'm just sort of throwing out and not giving you lots of details because there are tutorial questions which are pretty similar. And I think it's better that you get a chance to discuss these in your tutorial. I start talking about DFS forests. And if you remember back, there was a slide when I introduced the back edge or the tree edge or whatever. That's the sort of thing we're talking about there. How can we tell if we've traversed a DAG? Remember, DAG here is that directed acyclic graph. I'm not even going to give you any clues on that one. I think that would be a useful one to talk about in your tutorial. Let's change direction now. This time, just like we did at the start of the class, we introduced breadth first search, then we did depth first search. Well, we've done the algorithm for depth first search, so now let's do the algorithm for breadth first search. We know how breadth first search works. We go to the nearest neighbor first, and we process all of the nearest neighbors. That's one step away. Once we process them all at one step away, we go to 2 steps away. And again, we don't want to revisit nodes. So if we've already visited that node, we don't have to process it again. And so on. And we keep going using our rules again about the alphabetical order. So we always get the same answer. So as I process this, I start at A. The question again is always, who are my neighbors? My neighbors are B, C, D, and E. So I'm going to process them one step away in alphabetical order. Then, if they have other neighbors, we need to keep track of who B's neighbors are, who are C's neighbors, and so on. You'll notice this time the graph is a little bit different, just to illustrate the purpose. When I'm doing the depth first search, so this is basically mirroring what we had at the start of the class. Right? Typical depth first search, we go as far as we can in a direction. Typical breadth first search, we're sort of scanning or spanning out slowly, layer by layer, layer by layer. With the depth first search, that underlying protocol we used was that stack sort of idea in a recursive routine. Here in the traversal queue, we're going to use. So we're not going to use a stack. This time we're going to use a queue. That's the big difference between them. And in fact, we're not even going to implement this one recursively. What we're going to do is do it using an iterative approach using a queue. Just like the numbering system we used previously with Leviton, we're going to use a numbering system for the queues here. But remember, with the queue, we're going to put it into the queue, we're going to eject them in a certain way. So the subscripts here are corresponding to what Leviton does. So what happens? A is my first node, so I'm going to push it into the queue, pull it out. Maybe before I pull it out or at the time I push it in, I need to think about who are the neighbors of A. And I'm going to add them to the queue in an order. The order I add them in by default is going to be the alphabetical order. So I add all of the neighbors of A to the queue, B, C, D, E. And I take the first item out of the queue, the B, and then I'm going to be asking questions about who are B's neighbours and make sure all of those things are in the queue as well. And then I take that out and go to C. Who are C's neighbours? Make sure all of C's neighbours are in the queue. Oh, that's where the F comes from because I'm processing the C3. So the process is going to be pick a node. When I've got that node, somehow I have to get all of its neighbours into a queue. I'm taking the front item out of the queue, processing it, and if the order in which I do it, I have to make sure its neighbours were in the queue as well. That's where the numbers come from. When I'm talking about the breadth first search, just like we talked about before with the different types of edges, we don't have a back edge as such here, but we're going to have a cross edge, which is corresponding to nodes at the same level with that parent. So B, C, D, and E all have that parent A, and they're at the same level. So the cross edge is just corresponding to where they are in the actual graph. So here's our algorithm. Let's have a look at it quickly, and we'll see what happens. So this time, I'm not going to step through it anywhere near as much detail as I did the depth first search. The reason for that is because it's not a recursive algorithm, it's really just an iterative algorithm. I think most of us would be reasonably happy with it. And given that I've emphasized this idea of the mark before and the count, that shouldn't be a big issue. So my function breadth first search, I pass in a graph again. Same sort of arguments that I'm going to have this extra array mark to indicate whether I visited the node before. I'm going to use count in exactly the same way. What I'm going to do here is explicitly create a queue. Remember, in depth first search, I didn't create the stack, I used recursion. So I'm going to create a queue and initialize it, create an empty queue. And in our code we give you with Python, we show you how to do that. Now, what we want to do for every node in the graph, I ask the question always, have I visited that node before? If I haven't visited that node before, that's what the mark is used for. Increment this counter value and show the order in which I've visited the node. That's what the count is being used for. So if I haven't visited those nodes, what happens? I push it into the queue. Then, always while the queue is not empty, what am I going to do? I take it out of the queue and in effect, it seems as though I'm going to be doing something with its neighbours because I have to record the neighbours. So for each of its neighbours, for each edge adjacent to you, so we've talked about those words, what am I going to do? I'm checking whether I've visited that before. If I haven't visited it before, what do? I update it and then I inject it or stick it into the queue. So it's the same process all of the time. And that's where that number system comes from, back over here. So start with A, stick it into the queue. When I pull it out of the queue or at that particular step, it doesn't really matter which order you do that in, make sure you stick its neighbours into the queue. And we're always processing from the front as we go through. Let's stop sharing that one for a second and go again to the Python code for breadth first search. Just as we did last time, bring up the Python code for breadth first search. So the really simple graph again, which is the sample you have been given. Obviously, when we do breadth first search here, starting at node 1, we look for its neighbours, the 2 and the 4. So it looks like the order here is going to be 1, 2, 4, 3. Just as I did last time, I've just added one print statement and I get the correct order. Then, just as I did with depth first search, I've gone in and added print statements in appropriate spots in the code to print out the contents of the queue, so I know what is happening as I go through, and print out the contents of mark, so I can see what's happening as I process it. So just, again, strategically located print statements for the contents of the queue and mark, using the graph from the lecture slides, and you can see yourself, when you put those things in, you can see the order growing and the queue growing and shrinking as you move. So I'm going to come back to this again. Again, no apologies for not spending time and marking through all of these things. I'm sure you guys are capable of putting a few print statements into the code to see what happens. So I'm going to stop sharing that guy again and go back to our lectures. Actually, before the lecture slides, there might be a quick questions about something here. Let me scroll again for a minute. But the backtracking, there's a sensible question here from somebody about backtracking. Where do we record it? The backtracking part in the DFS stuff is coming about if you're going back to a node that already has a marked value, which is a non-zero. So you've already been there. It's that sort of argument that gets used. In the DFS explore recursion, we don't need an explicit base case because the for loop will eventually stop when the condition is no longer met. Well, in effect, the base case is corresponding to it's empty. All right, we've got a couple of slides to finish up with, which are essential for your assignment. So I would really like to get through these before we run out of time. A couple of comments just before we finish up with BFS. The complexity, it says it's going to be the same. Again, thinking about whether it's an adjacency list or an adjacency matrix. That question at the bottom is something that we come back to when we start looking at shortest path algorithms and a whole range of graph algorithms in about, I forget the exact week numbers, but about week 8 and 9. We're going to come back and answer a lot of questions like this. So how the course is structured, we introduce a lot of material, then we sort of put it on hold and we come back to it again later in the course. And the reason we do that is it gives you a chance to consolidate some of the fundamental ideas before we attack more challenging things. So for example, next week, we're going to come back and look at sorting again, which was introduced a few weeks ago. So we're always using that sort of approach in this subject. I'm going to skip that one because we haven't got time. Topological sorting. If you've read your assignment specification, you have a question on topological sorting. So I want to talk about it briefly for a minute. And in the last lecture, we talked about the classic scheduling problems and how, for example, it might have been the order in which you're going to build your house. And we had a trivial example about whether you have to put the windows in before you put the doors in, or it doesn't make sense to put the windows in if you haven't got a frame. So when I'm talking about topological sorting, what we're really trying to do is to come up with some sort of a linear structure, which is describing particular constraints of the problem. So we must have a directed graph. We must have a directed acyclic graph. We must have a DAG. So we need to have directed edges from A to B. And what this means is task A must be completed before task B. So it must be a directed acyclic graph. We assume that these tasks can be carried out by a single person. And I'm going to come back to that formal definition at the bottom in just a second. So here's my graph. We've chosen a relatively simple graph for illustration purposes. So if I was to look at that particular graph, we have to make sure we follow particular constraints. So as this stands, if I started at node B, because that doesn't have any inputs into it, so if I started at B, we can move off either to do A or D. We don't know which one has to come first, but we know that both A and D must be performed before we do C. And similarly, you cannot do F if you haven't done C. So what we're trying to do here is, given a particular graph of some sort, the graph must be a directed acyclic graph. Can you produce one of these linear flows so that the constraints are not violated? So what we're trying to do is we're trying to linearize the graph. That is the order of the nodes in that sequence, such that the edge VI, VJ, which is one of the edges in the graph, is always such that I is less than J. Topological sorting. The way in which we're going to do this, well, there's two ways we can attack it. The first way is going to be nice and simple. What we can do is take that particular graph, and it's a directed acyclic graph this time, what we can do is just perform depth first search. We've just learned how to do a depth first search algorithm. So I perform the depth first search and record the order in which the nodes are popped off the stack. If I record the order in which the nodes are popped off the stack, I can then list those nodes in reverse order. That gives me my answer. And it works because of that idea of the stack protocol and what's going on. Because you cannot solve the layers lower if you haven't done the layers at the top. So if UV is an edge, then it's possible to get this stack working. And obviously there's issues with ties and how we're going to do this sort of stuff. But the key is we do the depth first search, and then we think about the order in which they were popped off the stack, and we reverse that order. So if we have a practical example here, we have the same graph as we had before. I'm going to stop talking for 30 seconds and whatever. And can you just convince yourself that those numbers there are correct using depth first search? Using my rules about having a graph and processing them in alphabetical order. So I started with A, I asked my question, who are my neighbors of A, and so on, and I push them onto the stack. When I get to the stage, it's time to backtrack. That's what the red numbers start to correspond to. So I'm taking them off the stack. I continue on as far as I can go. I end up with the red numbers. I write them in the reverse order of which they'll popped off the stack. It gives me the linear order. So this is telling me B must be performed before D or A. Given the tie sort of idea, we're imposing what's going to happen as we move along there. So it's that sort of idea for topological sorting. So we can just do it with the depth first search, pay attention to the pop order, reverse it. Seems to work reasonably well. There's a second approach that we can use. An alternative method would be to repeatedly select a random source in the graph. That is a node with no incoming edges, list it and remove it from the graph. And when we remove it, we remove the other edges that's coming out of it. And that sort of approach is very natural, and we can basically understand it reasonably easily, and we can get an algorithm to work like this because it's basically a decrease and conquer algorithm. What we're going to do on your assignment, and this is one of your assignment questions, is I'm just going to scroll down to that question on the assignment, which is question 4. We're basically asking you to take that second version of the topological sorting algorithm by repeatedly removing a source. And I want you to describe an algorithm that we can use to solve this topological sort problem in this way. And where I've got described this algorithm here, you can do it in words, you can do it in pseudocode, you can do it in however you want to. I don't really mind. Describe an algorithm. Some of you might prefer pseudocode, some of you may not. I'm more interested in this question, and this is what your marks are really, where your marks are really going to come from, is we have an example graph here, a directed acyclic graph, and you're going to demonstrate your algorithm running. So when you write something in pseudocode or you write it in text and you demonstrate this algorithm running, I want to see, in effect, node by node, what is happening when you run the algorithm, and does it match what you've written? So that's where it's going to come from. So as it stands, the question is not super challenging, but I'm interested most particularly in whether you can do things in an unambiguous way. A last comment about assignment, and then I'm going to go to chat to finish up. I want to talk very briefly about submission and evaluation. You can all read the assignment spec in detail yourself. There's a few rules here. When you submit your assignment, you must submit a PDF document. That PDF document cannot simply be a photo or a scan of handwritten text. You must type your stuff up or use a text editor to do this sort of stuff. When we allocate marks to particular questions, obviously correctness is extremely important, but also, and perhaps equally important, is going to be how elegant is your algorithm, or have you communicated your ideas clearly? So if you write an algorithm, for example, that takes 10 pages and our sample solution takes 3 lines, there's no way in the world you will get full marks, even if your algorithm is correct. If we ask you to write an algorithm in a particular time complexity, you have to write it in that time complexity to get full marks. Where a question asks you to explain, justify, or describe, we are expecting you to write in plain English, not pseudocode, not any other language for that matter, but in English. Also, we've suggested word length. So if we've suggested you write a maximum of 100 words and you submit 3 pages, you will be penalized. You cannot write Python code in this assignment. The only acceptable solution for pseudocode for algorithms where it says will be pseudocode that follows the format that we've been using in the lectures slides or in your textbook, or indeed even on the assignment specification. There is pseudocode even in the assignment showing you where's the example. So Python code is not acceptable. If we get Python code, you will have a mark deduction. We are asking you to write the code in pseudocode. So I'm going to stop the recording there and see whether there's any questions from the chat. Obviously, there'll be more information on the discussion forum about the assignment as we progress on. What do you mean by doing by words? I'm not quite sure I understand the question, but perhaps I mean, if a question asks you to describe, I'm asking you to write some plain text, not pseudocode. Although if you really want to do pseudocode and add annotations, that's fine. Should we put print statements in Python code to demonstrate algorithm? No, if it's asking to demonstrate an algorithm, I want you to show me contents of variables, show me what the graph looks like at particular points in time. I can put a print statement and show me what's going on. That's not going to explain to me that you understand what's going on in the algorithm. All right, on that note, I think we're going, isn't BFS working for the topological sort? Well, that's an interesting question. How about somebody else can answer that one for you? I don't think it's going to, and you can think about the reason why. Because I don't think BFS is relying on that stack protocol in any way. All right, I'm going to stop recording there, guys. Have fun, and we'll talk about it again next time.